The previously discussed greedy algorithms would create a sequence of relations that we interpreted as the leaves of our left deep tree. What the greedy operator ordering algorithm is doing is different. We create trees, and these trees don't have to be linear. Here we also allow in general joining of joint trees, right? So we can create bushy trees. During the algorithm, we will see we have a set of relations in the beginning, and then we join relations to trees, and this set that is available for the next join to be picked. We do this picking based on the size of the intermediate results to be minimized. We will see that in a minute on the next slide. As input, as we have before seen as well, we have of course our set of relations R1 to Rn, and the output here should be a join tree. So let's see how the algorithm proceeds. This is our input, the number for the set of relations, we call that R. And before we start iterating, we assign this set to our variable t. This variable t is a set of relations initially, as we just initialized it. Later on, inside t, there can also be join trees. The idea behind t is that at every moment of the algorithm, t represents what is possibly there to be joined. So initially we have t consisting of relations. And as long as t has 2 or more ingredients, so trees or relations, we proceed and we pick the pair of joint trees, ti, tj, that is minimizing the cardinality of the join. You can see that in this argmin function call. We pick ti and tj, of course they have to be different, and we minimize the cardinality of the join. Then, once we have found this pair ti, tj, we remove ti and tj from t, and we insert the newly created join tree that is ti join tj. Okay, let's have a look at an example. So we have, let's say, R1, R2, R3, and R4 is our input. And now this is our set, and t would be initialized with this set. And now let's assume we find out by looking at these individual relations that the cheapest one in terms of the cardinality, so the smallest cardinality, is the pair R1 and R4. So now we will remove R1 and R4 from our set t, and then update t to be R2, R3, and R1 join R4. Right? And then we can go on with our new t here, and again look at all combinations of possible joins. For instance, R2, R3, R2 join this part here, R3 join this part, and so on. So all combinations, right? This is exactly done here. And let's say we find that the cardinality of R2 join R3 is the smallest one, and then that means we will remove R2 and R3 from our set t and update t by including now the join between R2 and R3. Right? And since there are still 2 entries here, and we cannot stop yet, but now it's simple because here we can see there's only one choice we can do. We are joining this join tree with this join tree. And this, in this example I've drawn, would correspond to a bushy tree because we are joining these two join trees. So this is not a linear tree anymore. Right? And that's of course only an example. Instead of joining R2 and R3 in the previous step, we could also have joined, let's say, R2 with this one here, and then in this case t would look like this, that we have R2 join parenthesis opening, R1 join R4, and R3 is still alone here, right, in that case. And then, of course, in the next way, we have disjoin this. And in this case, we see this would be a linear tree. So it doesn't have to be bushy, but it can be bushy, right? So we have more flexibility here compared to the greedy algorithms in the previous video. Still, however, this algorithm is greedy, so it does not guarantee to find the cheapest joint tree. Next, we will look at dynamic programming approaches to join order optimization. Dynamic programming is based on the principle of optimality formulated by Bellman in 1957, which states the following. Here you can read that. We will go in detail on the next few slides and see what that really means for our join ordering problem. The idea here is that if you have a optimal solution, then this optimal solution consists of optimal subsolutions for the corresponding subproblems. And this is very easy to see what that actually means for our join ordering problem. The idea when you're applying dynamic programming is to avoid redundant steps when you're executing your algorithm, and you do that by keeping track of optimal solutions, and you're using optimal solutions later on to find solutions to larger problems. And there's a little mistake you can do there, of course, but we will discuss this in a few minutes. So let's assume we have two join trees. These are all solutions to joining R1, R2, R3, and R4. So we have a problem of 5 relations. I want to find the cheapest tree. Let's assume we look at two trees now. This one and that one. You see there's like some differences here. Here we see R4 and R5 are joined last here as well. But here this part and this part here differs. Yeah. So the solution to this joint tree and this joint tree, they're solving the same problem, but the way they're doing is different, because here we join R1 and R2 first and then with R3, and here we join R3 and R1 and then with R2, right? So let's assume that we know that this join here, which solves the problem of joining R1, 2, 3, so it's a subproblem of our global problem of joining 5 relations. Let's assume that this one here is cheaper than we join R3 and R1 and then R2. So if we know that this is the case, so this red circled one is cheaper than the blue circled one, then we know when we're looking at these bigger join trees that this one here is cheaper than that one. Yeah? Because the solution for the subproblem here inside is cheaper for the first join tree than compared to the second join tree. And this is the idea why we can avoid looking at this problem here, or looking at this solution, if we know already that this one here is not the optimal solution for joining relations 1, 2, 3. Right? And that's the idea using dynamic programming or this principle of optimality for our join ordering problem. So more formally, the optimality principle for this join ordering problem says the following. If we have T, and we know T is the optimal join tree or an optimal join tree if there are multiple with the same cost, but let's assume it's just like an optimal one, no matter how many there are optimal, so there's one, T is optimal. That means there's no cheaper solution to joining relations R1 to Rn. So how does T look like? Well, T is a join tree. Here's a join, and there's 2 inputs. Well, this was not good, like let's say like this. So we're joining here because the join is binary. We're joining with our T tree 2 other trees, subtrees. If you're looking at this subtree here, then this subtree is solving also a join ordering problem, namely the tree here is a join tree joining relations which are contained here in this subtree. Right? If you're looking at all the relations, let's say there's R1 and R7 and R10 and so on, and more, in order to have T, so the entire one, to be optimal, this subtree here has to be optimal for solving the problem of joining R1, R2, R10, and so on. Right? If this was not the optimal subtree, we could find a cheaper one, but that means that the entire one is also not the cheapest, which would conflict that we assume that T is optimal. The dynamic programming solutions or algorithms we will see now are generating optimal trees bottom up. Initially, we look at all these single relations, and then we're creating and continue creating larger trees and making use of already computed optimal solutions for smaller problem sizes. Right? So again, if we have, let's say, this big relation or the set of relations R1 to R5, then inside this, we want to build a tree joining all of these. And we're looking inside this tree, and we have two subtrees which are joined. These individual subtrees represent subproblems. For instance, in this case, it could be that here we have R1, R5, and R4, and here we have R2 and R3, right? These were remaining. In order to keep the algorithm descriptions more compact, we will first introduce a very simple utility method called create join tree. Create join tree is just taking two join trees and finds the cheapest way to combine these two. Nothing more. There's like nothing really about dynamic programming hidden in this method. It just takes two join trees and tries out different ways to join these, and then returns the cheapest way to combine two given join trees. Right? It's like only a very simple utility method. So here is the create join tree utility method. As input, we have two join trees, T1 and T2, and a cost function C, for instance, C out, or some implementation-dependent cost function. And in case we assume we want to create only linear trees, then we assume here that T2 is a relation. Right? But in case of bushy trees, like nonlinear trees, T1 and T2 can also be joint trees, of course. The output is the joint tree, the best joint tree to join T1 and T2. So how does this work? Well, again, very simple. We keep track about different ways how we can join, and these different ways we keep in this set B. And so now we have two trees as input, T1 and T2, and we want to find the best way to join them. First of all, we know that there are multiple different implementations of a join: hash join, sort merge join, as a loop join, and parameters and variants. And here we go over all of these which are available and applicable, and we create for all of the different implementations different ways we can join. For instance, we can have these joins restricted to left deep or right deep, or we don't have any restriction, and dependent on this we have B extended by different solutions. For instance, T1 join T2 or T2 join T1, and we see if we're allowing only left deep trees, in this case this will not be executed here. And you see what's going on in the one here I just circled. We have T1 join T2, and if we're looking at linear trees, then T2 is a relation, and this is exactly what's happening if you're doing left deep trees, right? Okay, and so if there's no restriction, then you can also create any of these two, so T1, T2 or T2, T1, and in the end pick out for all the combinations. And note again, there's also different implementations you look at. You're taking the cheapest one. So you're taking the tree, the joint tree T that you just found, that you just created, which is minimal regarding the cost model. Right? So here you see an illustration of the search space regarding the principle of optimality. And this is important to see that this is only for linear trees. We don't create here any bushy trees, which are not linear. So what do you see here? At the lowest level, and I said already, these algorithms work bottom up. We have relations R1, 2, 3, and 4. And now we look at subproblems. First, of size 2. So we have here the subproblem R1, R4, and R1, R3, and so on. And then if we go further up in the tree, we have subproblems of size 3. Here, R1, 2, 3, R1, 2, 4, and so on, and R1, R3, and R4. And finally, in the end, we have our global problem we want to solve. So let's say this is just easy. We have only 2 options. If we have R1, R4, and R4, R1, and different implementations. So we solve this by applying the method before, and we have solved our problem. What's the best way to join R1 with R4? And now comes the dynamic programming part. We would store what is the best way to join R1 and R4. We do the same for R3 and R1 here, and so on. So that means we have solved the subproblems here and here. So we can look up in our dynamic programming table, more details in the algorithm soon. So we can look up in our dynamic programming table what's the best tree to execute the join between R1 and R4, R1 and R3, R1 and R2, and so on. So all of these. So how do we now take these solutions to create larger join trees? Let's consider this example here, this node. This represents the join problem of joining R1, R2, and R3. So what is now the best solution to joining R1, R2, and R3? Well, it's easy to see that there are multiple ways to join R1, R2, and R3. We can join R1 and R2 first, and then R3. We can join R2 and R3, and then R1, or R1 and R3, and then R2. This is depicted by these edges, right? So we would have, in order to find what is the best way, find or need to investigate all possibilities to join, but then we don't have to go deeper and see what's the best way to join R1 and R2, because we can just look it up in our already pre-computed table. And if you want to join R2 and R3, you don't have to now again investigate, because we can just look it up because we already solved the subproblem here. Right? Still, we have to go through all the combinations to join R1, R2, and R3. And that's maybe a common mistake, what I have seen in the previous years, because it's not true that we can just take 2 optimal trees and put them together and have the optimal larger tree. But we have to test all possible ways to take optimal trees, and from all of these ways we take the cheapest larger tree. To illustrate this, this is here for this one we have an optimal tree, for this one we have an optimal tree, for this one we have an optimal tree. So these are all here. For each of these we have the optimal tree solution already, right? And if you want to find the optimal solution here, we cannot just say, well, take R1 and R2, they're optimal, and R3 anyway is optimal because it's only one relation. And this is not the way, this is not enough. We have to really try all possibilities here. And of course, we do the same for this one here as well, for joining R1, R2, and R4. So we go and test all ways how we can do that. We see here, we can test, first of all, we have to test the solution of taking the optimal plan for R1 and R2, and then joining R4. Or we take the best solution for R1, join R4, and then joining with R2, and so on. And this is the last one here we have to check. So joining R2 with R4, and then take additionally R1. And we have to test all of these 3 possibilities, and then for the cheapest one, we will write it down in our dynamic programming table for the best solution for joining R1, R2, and R4. Right? And now we go further up. This is our global problem we have to solve. And again, we have to now test all possibilities we have, all ways we have to join R1, R2, R3, and R4. And you see here in the set notation we have, like here and here, these are not join trees, right? These are only the subproblems. Or here you have the global problem, of course, right? So these subproblems are just sets of relations that need to be joined, and we have to find the cheapest plan, the cheapest join plan, cheapest join tree to do that. So looking at this global problem, R1, 2, 3, and 4, and we have already pre-computed all of these optimal solutions for the subproblems. Still, we cannot just go there and say, we have 4 relations, R1, 2, 3, and 4. Let's just take the best tree for this one, and we just join R4 in addition. That's not how it works. We have to test all of the combinations. We have to look at the cost for taking this, or the solution for this problem, plus joining with R4. We have to get the cost for looking at this solution, the cheapest one that we have pre-computed, and the cost for joining with R3. We have to also look at this here, this subproblem. We know what is the best tree because we have just pre-computed this earlier and stored the tree in our dynamic programming table. So we know what is the best way to join R1, 3, and 4, so we don't have to do it again. And in order to find the cheapest one here, we have to now see what is the cost of this joining R2. And it's still not done because we also have to consider when we have the cheapest plan for R2, R3, and R4, and we have to consider joining with R1 to make our global problem done. Right? So this is not to be like, or this is like the way it works, and it's not the case that if you're taking 2 optimal trees, which are optimal for subproblems, to any of these, and you're just joining them, this does not mean that the resulting tree is optimal. Right? This is important to note. And again, this is only for linear trees, for left deep trees in this case. Okay, more formally, said this already, we want to create left deep linear join trees. And if we have such a tree that has more than 2 relations inside, we can illustrate this or write it down like there's a subtree T prime joined by a relation Ri. And this T, the larger tree T, is by 1 relation larger than the subtree T prime. If T is optimal, then T prime has to be optimal too. Yeah, this is what the optimality principle says. So if T is optimal, but T prime would not be optimal, we could replace T prime by the optimal tree for solving the same problem as T prime is solving, and then T, or we found a tree which is cheaper than T, which is like conflicting the assumption that T is optimal. So if T is optimal, then the subtree T prime has to be optimal too. Now if we consider, let's say, T to be the join tree for relations R1, 2, 3, 4, and T prime is the solution for joining R1, R3, and R4, in that case Ri would be R2, right? And we cannot just look at this only, but we have to look at all combinations of looking at subtrees T prime with the one more relation Ri. Right, so we have to test all optimal T prime plus this relation in order to find T. This is exactly illustrated on the previous slides, right? So we have to test really all possible ways to construct T based on optimal T prime and one more relation, right? But the point is, I cannot stress it enough, that we cannot just take any optimal T prime and this relation. We have to test, we have to join or test all possible optimal T primes. And the idea behind dynamic programming is that we have, like in the previous example, we have stored for t prime, not for t prime, but for the relations in t without Ri, we have already stored and pre-computed the optimal tree t prime. So we don't have to now do it again. We can build our optimal trees by looking at optimal solution for subproblems, but we have to look at all possible ways to combine these sub-solutions, subtrees, for the sub-solutions to our larger tree. One remark about notation: when we're talking about joint trees T, the cardinality here represents the number of relations inside T. Here we do not denote by this the size of the join result. Right? This is important to note. The sets later on, S, S1 and S2, there are sets of relations, so our subproblems.